In this chapter, we will be studying limits. In this lesson, we're going to be looking at the behavior of infinite sequences and seeing how that can help us find the limits of regular functions.
Okay, hi everybody. So in this lesson here, we're going to take a look at infinite sequences. Okay. Now, remember that a sequence is just a pattern of numbers that obey a specific rule. Okay. So a rule for letting us move from one value to the next, to the next, to the next. And usually they're going to look something like this when we write them out here. We'll use, for example, S to represent the general term in the sequence, usually with a subscript. Okay. Now, the significance of that subscript is merely to tell us which term in the sequence it is. That's why we let n be an element of the naturals. And so the numbers we're looking at here are like 1, 2, 3, 4, and so on. Okay. And so if we were looking for the 23rd term, this would be S sub 23. Now, oftentimes, the terms in a sequence, okay, can be found by simply knowing where in the sequence they occur. So if you wanted the 23rd term, you would simply multiply 2 by 23 in order to get it in this particular case here, in this particular sequence. Another sequence might look something like this, or it might be AB, and those would be constants to the end. And again, n is an element of the natural numbers, so that we're linking the term, the value of the term, to its position in the sequence. But in this case, you'd need to know what A and B are for that to work. Now, you've looked at sequences before. There's nothing new here. You've seen those back probably in your grade 11 math course here. All we want to do is we want to take a quick look at what happens to some of these limits, or what happens to some of these sequences as we let the n value go off to infinity. And there, hence, we talk about infinite sequences. Okay, and this becomes really important in understanding calculus, or at least it can. Unfortunately, in this particular course, we're not going to go this particular direction, but it is possible to link all of the ideas that you're about to look at in calculus to this idea of an infinite sequence. In fact, I would love to spend a lot more time on this, but it's probably an idea that I'll have to kind of swing back to show you what's going on. Anyway, so let's talk really quickly about reciprocal limits. And all we're talking about here is what happens when you take that x and flip it over here. Now, this could be, for example, this could be a sequence of numbers. We could let x, for example, be an element of the naturals here. And essentially what we're going to do here is we're going to let x, or n in this case, go off to infinity. So what happens to a fraction here when the denominator gets larger and larger and larger? Well, the truth is its value gets closer and closer and closer to 0. Okay? If you let x go off to negative infinity, which again, if this was a sequence, we could very easily do that simply by letting x be n here, then one of the natural numbers, and we just put a negative out front, and then let n go off to infinity. And that's the same thing. Now, the issue here is, in this case here, as I let x go to infinity, yeah, the value of this term is approaching 0 for sure, but it's doing it from above. Because we're talking about positive infinity here, 1 over x will always be a positive number. So for example, if this is your x-axis right here, what's going to happen is this graph's just going to drop down to it, or the value of the terms in the sequence are going to drop down to it. Here though, as we go to negative infinity, if this looks like your x-axis here, what we're doing essentially is we're coming up to the x-axis from below. A couple others that we should look at here. If x is going off to infinity, and we've got 1 over x to the r, as long as r is a positive value, okay, as long as it's a positive value, then 1 over x to the r is going to approach 0. Okay, now I want you to think about that, because if r is less than 0, just think about what that does here. If you've got a negative in the exponent here, what that'll do is that'll cause that to reciprocate. And essentially, this is going to pop up into the numerator. And then at that point here, as we let x go to infinity, the whole value is going to go to infinity. Here, we're going to let x go to infinity. We've got r to some x here. Now, we got to be careful with this one, because you can see here there's two different limits where I'm dealing with something that looks exactly the same. The only thing that's changing here is r. So if the absolute value of r is less than 1, not even including 1, it's got to be less than 1, okay? As long as you're dealing with some sort of fraction here, then what happens is as you let the exponent get larger and larger and larger, the overall value is going to approach 0. Now, if you're not sure about what I mean by that, let's just take a quick look at what I'm talking about. Let's say, for example, that you've got, just wait for this to load here. You've got 1 over 2, okay, and we're going to take this to the power of n, and then we're going to take the limit as n goes off to infinity. Well, think about what this means here. What we're doing here is we're increasing the value of n. So you're going to get a half multiplied by a half, multiplied by a half, multiplied by a half, and so on and so forth. And think about what that half does. Okay, when we multiply it by when we multiply this half by this half, okay, we're going to get a quarter. Multiply this by this half right here, we're going to get an eighth. Multiply that by that next half there, we're going to get 1/16. Notice that the denominator gets larger and larger and larger, which means the overall value, 1 over that denominator, 2 to the n, that's going to get smaller and smaller and smaller. It's still going to stay positive because any power of 2 there is going to be a positive value, but it's going to drop in value and it's going to drop and approach 0. Like, once again, the larger the denominator, the smaller the overall value. And as long as you're dealing with numbers, so here's our number line, here's -1 to 1. As long as we're talking about numbers, okay, within this little zone right in here, okay, between -1, whoops, I want to write it like this, between -1 and 1, then you are going to get situations here where those numbers are such that the denominator is larger than the numerator. Okay, if you can write them as a fraction. Okay, that's just the way that's going to work. So that's what we get. Here. Now, on the other hand, if r is some value greater than 1, okay, and we plug that in here, for example, let's say 2, then as you let the exponent get larger and larger and larger, what that's going to do is that's going to go off to positive infinity. Okay, 2 squared, 2 to the 4th, 2 to the 8th, 2 to the 10th, 2 to the 100th. Those numbers are just getting larger and larger. Now, the reason why we put plus or minus infinity here is if you've got a negative is in the base there, then what happens here, now let's just think that's -2. So here's my number line. Here's at the x-axis. -2 squared is going to be +4, but -2 cubed is going to be -8, up to +16 when I take it to the 4th power, down to -32. And so what happens here is you end up with these dots going up, but also these dots going down. And so if r is negative, this thing is alternating, okay, between the positive and negative. And in fact, we would call that an alternating sequence. Most important, though, for what we're trying to accomplish right here is essentially what's being drawn in this graph right here. When we're dealing with a sequence, okay, and just very, very straightforward, 1 over n, and we're going to let n be a natural number here. And so as n gets larger, so right here, n is 2, sorry, here's n is 1. So we get 1 over 1 is 1. There's my y-coordinate right there. Then this is where n is 2, n is 3, 4, 5, 6, and so on. Notice there's no in-between values, and that's totally okay. But notice that what happens here is that the value drops, gets closer and closer to 0. It will never equal 0. Okay, it's important to note that. It will never equal 0. It does, however, get closer and closer to 0. And so we can say that the limit as n approaches infinity of 1 over n is going to be equal to 0. We can use that particular outcome to help us solve for more complicated limits. And that's what we're going to do right now. We're going to take a look at how we can utilize this idea to make some more complicated looking limits a lot easier to do. Okay, everybody. So let's take a look at some limits now. Let's just start off with a really straightforward one here. So we're going to take a look at the sequence Tn is equal to 1 over n plus 1. And we're going to ask about the long-term behavior of this particular sequence right here. What does it look like as you let n go off to infinity here? And we might start off by noting that this sequence here, when n is equal to 1, it's going to be 1/2 the first term. N is equal to 2 will be 1/3, 1/4, 1/5, whoops, and so on. Okay, anytime you stop, no matter where you stop, the denominator is always going to be 1 more than the number of the term that you stop at. And then we would just let this go on forever. Now, I want you to notice here that this is very, very similar to that limit that we were looking at just a little bit earlier here when we let x go off to infinity of 1 over x. The only difference between this one right here and this one right here is our starting point. This one, okay, would have started at, would have started at 1 over 1, comma 1/2, comma 1, and so on. This one doesn't. Now, that would mean that this guy right here, okay, this one right here is a subsequence to this one over here. They just don't, the only difference between them is we're missing that one starting point here. But because this one goes to 0, okay, eventually this thing is going to approach 0, and we can assume the same thing about our sequence up here. So when we take the limit as n goes to infinity of 1 over n plus 1, it's going to behave very, very similar to this one, almost identical to that one. So that one is going to go to 0 as well. That's an important result, really important result. We're going to use this a little bit later on here. But this also tells us one other thing, okay? And so this is just a word of warning to all of those here. I mean, you often hear this little fight that happens in the school ground, right? I'm smarter than you. I'm like 100 times smarter than you. Someone goes, I'm 1,000 times smarter than you. Well, I'm 1,000,000 times smarter than you. Then I'm 1,000,000,000 times smarter than you. And then someone says, well, I'm infinity times smarter than you. And then this person over here, almost always you'll hear this. Well, I'm infinity plus 1 times smarter than you. Listen, based on what we just saw, this person loses. Okay? Whoever gets to infinity first, there's your winner, because infinity plus 1 is just infinity. Okay, it's the same thing. So basically, we're equivalent there. Now, if you really wanted to kind of prove that you were smarter, maybe what you would do in a case like this is you'd say, you know what? I'm infinity minus 1 times smarter than you. Now, if you say that, your friend over here is very likely going to look at you and go, what? Because they won't know what's going on. And as soon as you see that face, you'll say, ha, I am smarter than you because I know what's going on. Anyway, let's take a look at another example. Okay, everybody, let's take a look at another limit here. Let's take a look at the limit as x approaches infinity. Let's make it x squared minus 2x plus 3 all over 2x squared plus 6. Now, what we're going to do here to help you out with this, I'm going to show you a little tool that you can use here. Actually, maybe I'll clean this up. We'll do it down here. This is going to be equal to the limit as x approaches infinity. Now, what we're going to do here is I want to use this little tool that we've just been introducing, this behavior of this reciprocal limit, this 1 over x or this 1 over n. We want to use that to help us understand what the limit of this rational expression is going to be. The trick to doing this, and it's actually quite simple, is to take this question and make it look like something that I've already seen before, or at least make the pieces of it look like something I've seen before. So I don't know how to deal with this x squared up here, this negative 2x plus 3, 2x squared plus 6. But what I can do with this is I can multiply by 1 over x squared. What I'm going to do is I'm going to purposely choose the largest power in the denominator. Okay, 1 over x squared, 1 over x squared. Because I'm choosing the largest, I'm going to use the largest exponent, let's say, exponent in the denominator. I know that when I multiply that through, specifically in the denominator, when I multiply that through, 2x squared multiplied by 1 over x squared is going to give me 2. I haven't got a problem with 2. 2 is fine. But what's nice about this is that 6 becomes 6 over x squared. Okay? Up in the numerator, that x squared is going to become 1. That negative 2x is going to be minus 2 over x. And that plus 3 will become 3 over x squared. Now, bear in mind that what I've multiplied by here is just 1. 1 over x squared divided by 1 over x squared is equal to 1. Unless, of course, x is 0. But you know what? That's not even an issue here because I'm letting x go off to infinity. So that's not a problem at all. Now, look what happens to each one of these little pieces here. Because I'm taking the limit as x goes off to infinity, okay, as x goes to infinity, this piece right here, we've already seen is going to go to 0. Now, multiplying by 2 isn't going to alter that. Over here, each term here divided by 3x squared, each term is going to be divided by x squared by a number that's getting larger and larger and squaring it on top of that. So in fact, this is going to go to 0 even faster than the 2 over x. In the denominator, the 6 over x squared is also going to approach 0. So what happens here is as x goes to infinity, now granted, you never get to infinity, but it's a matter of degree, everybody. It's a matter of degree. As x gets large, this ceases to have an impact. So does this, so does this. The terms that have the largest impact are going to be these ones right here. And so what happens at the end there is that our what survives out of that are simply the numbers 1 and from the numerator and 2 from the denominator, 1/2. Okay, that has a lot to do with just the behavior of the function here. So just to describe this again, x squared minus 2x plus 3 over 2x squared plus 6x. To give you another way of thinking about this that will maybe kind of highlight maybe more poignantly what the limit is doing, let's assume that x is money. Okay, let's say it's money that you have on you right now. Now, if x is $10, or let's even smaller than that, let's make it even better. Let's say x is $2. 2 squared is 4, minus 2 times 2 is 4. Well, that goes to 0 right away, and plus 3 in the numerator. 2 times 2 squared is 4 plus 6 is going to be 14. So that's like 3 over 14. Now, you might not quite see where I'm going talking about money right now, but you will in just a moment. Anyway, at that point right now, throwing in $2, the numerator and denominator are kind of having a huge impact on each other. But watch what happens here. Or sorry, I shouldn't say the numerator and denominator. What I should be saying is this minus 2x term, this plus 3, this plus 6. These are having huge impacts. But now think about this. Let's let x get really, really big. Let's let x, for example, be like $1 billion. If you had $1 billion squared, a billion billions, and you lost 2 of them, would you care? Probably not. And if someone said, "Oh, you poor person, you lost 2 of your billion billions. Here's $3." Would you care? Probably not. When x gets really, really large, terms that have smaller degrees have less and less of an impact. So even the denominator, that plus 6, is going to be basically irrelevant for extremely large values of x. So what happens here is what dominates the behavior of this rational tends to be the highest degree terms. Now, x squared over 2x squared, how does that behave? Well, that behaves like 1 over 2, and so that becomes our limit.
Now we're going to take a moment to discuss how what we've just seen can help us deal with other questions.
Okay, so now in general, what we can do is talk about the behavior of the limit overall, but we can use a bit of a shortcut. If you saw what I just did there, we can actually apply a rule here, and you have very likely seen this before in a previous course here. But as you're letting x go to infinity or plus or minus infinity, and you're dealing with a rational, because it's almost always the rational that we're interested in how it behaves, because the numerator and the denominator can offset each other a bit. If you've got a times x to the m, and then it doesn't matter what comes after that, don't worry about it, and you're dividing that by b over x to the n, and then again, it doesn't matter what comes after that, because remember, these are the dominant terms in the numerator and denominator. We're assuming that this exponent here is larger than every other exponent that we've got with every other term in that numerator. Same thing down here in the denominator, that the n is the largest exponent of all those terms. So these are the dominant ones. Everything else is irrelevant. So now if it's the case that m is larger than n, so in other words, the numerator is growing quicker than the denominator, then when we when we plug in, when we multiply by 1 over the largest limit in the largest exponent in the denominator, the numerator survives. Now, just to illustrate that, let me show you what I mean. Let's grab a really quick little example here. Okay. So let's say, for example, that we've got x cubed plus 2x squared minus 5 all over x squared minus 1. So when I want to take the limit as x goes to infinity, now what I just showed you here is we would take the largest exponent in the denominator, and I would multiply numerator and denominator by 1 over that largest exponent. Now, when I multiply that through, we're going to get the limit as x goes to infinity. Multiply that through x cubed multiplied by 1 over x squared. That's going to leave me an x. Here, the x squareds will cancel, so we'll be left with 2. And then minus 5 over x squared. In the denominator, we're going to get 1 minus 1 over x squared. Now, as I let x go to infinity, yes, this term is going to become less and less of an issue. So is this term right here, less and less of an issue. But look at what happens here. My numerator is going to go and become infinity plus 2 divided by 1. Well, that's just going to be infinity. That's not going to get any better. Okay? So that's essentially what that particular little rule is trying to get at there. Now, if n is greater than m, whoops, sorry about that. If n is greater than m, then what happens is that we're going to get a limit of 0. So now that's what happens if the numerator is, let's say, x squared and the denominator is x cubed. Okay, let's take another little look and see if we can make sense of that. Okay, just waiting for this to come up here. So let's say we've got x squared, plus 2x minus 1 over, let's just say, x cubed, just for argument's sake. So we're going to take the limit as x goes to infinity. So I'm going to multiply numerator denominator by the largest exponent that I see in the denominator. When I multiply that through, this will become the limit as x approaches infinity. This will become 1 over x plus 2 over x squared minus 1 over x cubed, all over, and the denominator will become 1. Now, notice that in this case right here, this is going to go to 0. This will go to 0. This will go to 0, but the denominator doesn't. In the case where the degree of the numerator is smaller than the degree of the denominator, it will always behave like this. This is going to go to 0. Okay? So that's kind of a neat little result there. And finally, if the two are the same, and this is the example that we did just a few seconds ago where we got 1/2 as a result. If the m and the m are the same here, like x squared, then the limit becomes that ratio of leading coefficients. When I multiply by 1 over the exponent x squared, 1 over x squared, these powers here disappear, and all that survives are those leading coefficients. Okay, so this is a handy little rule. And again, you probably learned that in an earlier course. I know that I show my students this when I teach them the grade 11 course, and we start talking about rationals. But other than kind of an awkward explanation as to what happens when x gets larger, we don't really talk about limits there. This is really where this idea kind of makes the most sense, and we can do something with it and explain why the rule works the way it does. Okay, we're going to do one more here. We're going to take the limit as x goes to infinity, and we're going to make this 3x minus 2 multiplied by x plus 1. Oops, I don't know why it doesn't want to do that. Over 2x plus 1, 2x minus 1. Okay, now I'm going to do this in two different ways here. Okay, I'm going to do this kind of the long way first, then I'm going to show you a shortcut for doing this. So to start off with, we're going to get the limit as x approaches infinity, and I'm going to expand out the numerator here. That's going to be 3x squared. That's going to be 3x minus 2x, so plus x minus 2 all over the denominator. Well, that's a difference of squares there, so 4x squared minus 1. I notice that when I look at this, that I've got this rational expression. The largest exponent in the denominator is x squared. So I'm going to multiply numerator and denominator, each term there, by 1 over x squared. And because I'm doing it to both the numerator and denominator, the result is I'm multiplying by 1. So the result's not going to change the behavior of the rational. So my numerator is going to end up being 3 plus 1 over x minus 2 over x squared, all over 4 minus 1 over x. And now, x squared. And now, because we're letting x go off to infinity, I know that this term is going to become less and less important. So is this one, so is this one. And we are going to be left with nothing but 3 over 4. Now notice again, I don't write the limit again. I don't write limit as x goes to infinity. I've taken the limit. There's my answer, 3 over 4. Or we could have done this. This is the limit as x approaches infinity. Another thing that I could have done here is I could have noted, okay, that when we've got 3x minus 2 times x plus 1 over 2x plus 1 multiplied by 2x minus 1, I could have noticed that I've got two linear terms multiplied together, two linear terms multiplied, or factors multiplied together. I know that the numerator is going to become a quadratic, and I know that the denominator is going to become a quadratic. So without multiplying out everything, all I really need to do is figure out what the quadratic term is in both cases, because those are going to be the terms that dictate the behavior of the entire rational. So 3x times x is going to be 3x squared plus blah, blah, blah. Don't care. The denominator is going to be 2x times 2x, which will be 4x squared plus, I don't care. I don't care what else there is. I only care about the terms that are going to dominate the behavior in the numerator and denominator. Now, because the degrees are the same, all I got to do is look at the leading coefficients here, and the leading coefficients are 3 and 4. And so as a result, I know that my limit would be 3/4. Just as a nice way of taking a shortcut through that particular problem.